That's good. Yeah, grad school is fun because you get to travel for free. That's one of my funnest, like, I don't know, going to conferences and like really getting to like say, oh, I went to Paris. How'd you go to Paris? Oh, for work. That's kind of like a fun flex. Uh, wait, grad school um, it's six. It's six, it's right. Can you help me get over to six? Is that six? All right. You see slides here? Those the right slides? Atmospheric structure. Let's fucking go, boys. And people. Okay. Enable. What's the enable one? Is it below? Okay. Well, well, well. Look whom it is. Okay. Which one is the SODI? Up. All right. Hey, that's pretty good. 20% success rate. Let's pump those numbers, boys. And people. Okay. Um, make sure that I'm recording audio. Okay, I'm recording audio and I'm screen sharing. So technically I'm doing everything right, except for I'm not on time. We're not going to talk about that. So, oh, everything okay? Is that water? Oh, thank God. Okay, so we were starting off having a discussion about atmospheric structure. Okay. And even if you don't necessarily go into atmospheres, it is really helpful to see how this section works. It talks about fluids, and if you care about the interiors of stars, you'll need to know this as well. So without any notes, put your notes down. For you guys, you'll just be screwed unless you watch the lecture, which I'm not banking on. Okay. Do differential time. Okay, what's this? Ah, not you guys. What's F? Great question. What? I said a function. A function. Yeah. It must be a function, right? What function? What is that? Only one function can do this. David? E to the x. E to the x. Only one function whose derivative is its function. That is actually the definition of e to the x, in case you didn't learn how to derive. Okay. What about this one? Here. AX. What's another way of thinking? What is the name of this equation? Yeah, so when we take a double derivative of something and we get the thing back, canonically, this is a wave. The wave equation has two derivatives in space and two derivatives in time, right? But the solution here can be exponentials and complex exponentials, particularly if I do something like minus f. Because two derivatives, right? If you notice here, e to the minus x, two derivatives of e to the minus x could never give you minus f. The only way you get minus f is if you have, oh, not E to the E, that would be in Sam. That. Right? And of course, you may see this in many times in your life as sines and cosines. The sines and cosines are just the four persons E to the IX. Okay. Ready for math now? Okay, since you're all present, I will repeat, do the SOTIs. Okay. All right, this is why we used it. So we found a relationship that was a differential relationship between the pressure and the density. So as I go up in altitude, how do these quantities change? And on one side, I saw something like, let's write the original differential again. dP dz is equal to, remember what the original differential is? What's the left-hand side say? Just in English? Right, and what happens? Vertical, right, so the vertical change in pressure is due only to yeah, it's certainly going to be due to its position, right, as a function of the position, but that's not the physical cause of the change. Remember that the differential, so like if I get something like this, P as a function of Z, this tells me the functional relationship between variables, specifically one that is dependent on the other, right? But it doesn't tell me the physical relationship. Differentials tell us why something happens. Encased in here is the physics itself. So pressure changes as a function of height because of another term. You remember what that is? There is pressure that comes in later, but that's not how we originally wrote it. You're right that that's where we get to, but it's not the first step. In fact, we wrote it like this, minus G times rho. Now I did that backwards. We wrote G. Here, minus rho G. Okay, so what does that say? That says that the pressure changes with height as a function of the density. Right? We're going to assume that G is a constant wherever the body is. And we just said that it depends only on the density. Right? The density, that is to say, how much the density is changing with height, tells you the difference in pressure over some area. Okay, and then we said something about the density. How do we relate the density to the pressure? Good. Now we're going to use the rich man's ideal gas law, not the chemist's ideal gas law. So how do I write that?
Rich man's ideal gas law.
Well, there's two ways to write. How would you write the ideal gas law in your physics 2500? Good, and that's gross. And I don't like that because V is a gross quantity. Right? V is for chemists who measure boxes. We don't measure boxes in physics. Is it rho P? Exactly. Rho K T. Right? This is equivalent to the same as PV equals nRT, but even that's disgusting, right? No one wants an R. Hey, that's physics. Physics is KT, right? And actually, we have to be a little specific. We have to add that in there, but I just went ahead and I ignored that. It's in your notes, but it's just more letters that I don't want. Okay. So now we can replace this with P and we get what?
So we get P over KT.
Right, so we're going to write G over KT is the stuff in front times P. Right? And that's how you get your expression. Okay, and that was one way to solve it. You could, of course, integrate and you would get the same solution. And then at the very bottom, we did some stuff with the fact that we need the right dimensions and yada, yada, yada. And we made up this little definition. We called it H. And H we wrote as KT over G. I think actually it's mu G. You want to be very specific. Okay, where mu is like the mean molecular mass. Okay. Now, what does this thing mean? The H mean, just typically. Height. Good. So this is a capital H, so it must be a specific height. And in fact, we call this the scale height. Because this is an exponential, this solution, P, is equal to P naught at some fixed pressure, e to the minus z divided by h. Okay. So when your vertical altitude gets high enough that you have gone 1, 2, 3 scale heights, then you're dividing your original pressure by 1 over e. Right? That's how we interpret that. And of course, 1 over e for a physicist is 1 over e, a third, right? Because e is 3. Now it's 2.8, but you're not going to hold a gun to my head. Okay. Okay. Good. So that's the definition of a scale. And when you can define the system as being in hydrostatic equilibrium, right? That's this statement right here, hydrostatic equilibrium. Then by definition, you have what's called an exponential atmosphere. Is this valid everywhere? No. Is it valid even at very fine approximations? That is to say, if I took a weather balloon, right, and I tied to it a barometer that measures pressure, and I sent it up in Earth's atmosphere, but I get a nice scale height over the first 10 or 15 kilometers. Experiment. That's the right way to feel about it, right? Typically, we take a very complicated subject and we simplify it to one dimension, and we don't let the fluid move, right? In practice, have you ever really stood on Earth with no motion of the fluid? No, you always have this thing called wind, right? And so, at first approximation, right, we may say something like this about the pressure going up, right? But that's probably the average quantity. And maybe it looks like this, right? Okay. Why would it look like that? Yeah, but we're going up in altitude and the pressure goes up. Have you ever heard this word low and high pressure system? Yeah, it could be a storm. So for example, in order to create a hurricane, you have to raise hot water. And as the hot water rises, it actually heats up, and you can get local pockets of warm air. And you can get high pressure systems. Right? So this is a completely valid line, but it's a second order effect. Right? The first order, many atmospheres at least slow down our exponential scale heights. Good. All right, let's get more complicated. Here's the scale heights. Here, hold on. There. Here's the scale heights for some planets that you know and love. That's us. Now I know you haven't memorized what 8 kilometers feels like. Or have you? It's like 5 miles. So this is for an isothermal scale height. And if you've ever heard that, you know, like going to a place like Tahoe or a place like Colorado, it's hard to. And so you may be saying to yourself, that seems like a really large scale up. Right? Well, it actually is much larger than the one that we feel, because if you go up to say Tahoe, you actually are getting about 20% less oxygen. Because the air density itself has gone down by about 20%. And the reason for that is this approximation is a bad one, right? The ideal gas law is not applicable in most atmospheres. Again, first order approximation, so we understand the vertical profile, and then we can go on from there, right? And the first order, we can look at all of these and we can say, like, here's Venus and Mars, they have a very similar scale height, as thermal scale height. Most of the terrestrial planets is around 10, right? So I mean, like a stronger planet. Jupiter got a massive one, 27. Saturn's is even bigger. And to understand the role here, how do you make H big? What? T big or G small or? Okay, it's not, can't do anything with that. This is the mean molecular mass, right? So if I make this small, right? So let's take a hydrogen atmosphere and let's put it on a couple different planets. Okay. Hydrogen atmosphere on Earth has a bigger or smaller scale height than at Jupiter. Quite big. But we haven't calculated it yet. Yeah, so actually I was just thinking here about temperature. Okay, as I move towards the sun, atmospheres tend to get warm, right? Because that's the driving component for every atmosphere. Okay. So why then are the terrestrial atmospheres so much smaller than the big gas giant atmospheres? What? It's not hydrogen. Absolutely, right? So molecular mass goes up. Now it's this denominator that's really hurting us. Because the G's actually can be quite comparable, strangely enough. You know, Jupiter is much bigger, but it's also much more massive, right? And if you write how G is, it's something like M over R squared, right? Not just M. Okay. All right. Cool. They're not that different in size. We get that. I think this is actually incorrect. I should recalculate this. Now that we've gone to Pluto, New Horizons, I think that they have, yes. Okay. This is good. You know, these values here, especially if you care about modeling, these are good enough to show that this idea of a plane parallel approximation, that is to say, can you model the Earth's atmosphere as flat? That's usually good for local areas, right? Which is very convenient if you have a computer at home, because your computer likes to do boxes. It does not like to do curved surfaces, right? It doesn't know how to do that without applying an isothermal mapping, right? Okay. All right. This wasn't last week, this was a long time ago. We talked about transporting radiation, energy by radiation, conduction, and convection, just like at the beginning of class. What are each one of these? What's radiation again? Nope. That'd be radioactivity. Very annoyingly, the same word, and I can explain the history if you care about that. But this word right here is right by what? Right, these are all heat exchanges, that's true. But what is the process? What? Emitting is the word I'm looking for, because these are all heat processes, right? But remember that radiation means light, Now, it can be infrared light, it can be UV light, but the idea of getting rid of heat through light is the most important part, right? The first part is light. The second part is, what does conduction mean? Contact of what?
Hot object, cold object.
Good, but why? We understand, like let's really break down what the physical phenomenon is. What? Through what process? Why does hot go into cold when you touch them? Entropy is how we describe it, but the process is collision. You have individual particles smashing into their nearest neighbors. Okay, so in a hot thing, those particles are moving quickly. They may be in a matrix, but they're still moving. They come into contact with the cold thing, they start moving the cold thing. And that propagates through moving the other objects, right? So this here is absorption and emission of photons, of light. This here is molecular collisions, atomic collisions. Okay, and now we say to ourselves, well, we've covered all of it, right? Nope. What is convection? Yeah, exactly. And the process here, this one is the least obvious. This is something called bulk transport. Okay, you can heat something by moving a lot of it elsewhere. Right, that's not a very good definition, but if this is a really hot table, right, and you're asking me for the temperature in this area, and I take the hot table away, it gets cooler. Right? Okay. So the first one is photons, the second one is collisions, and the third one is bulk transport. And in fluid, especially in atmosphere, they're all fucking working. Okay, so let's take a piece of hot gas, let's bring it up to a new altitude, and then you leave it there. Okay, as you do that, it now exchanges heat with its environment. How does it do that? Collisions with other gas particles. And because it emits infrared radiation, it heats up your environment. One of those might be dominant in different locations. Right? This may be visible, right? Convection may only happen in certain parts of the atmosphere where certain conditions are made, right? So you have to consider all of these when you think about fluid. Okay. Is the transport of energy due to density differences? So the only time this is not true is when you're in microgravity, and we will not be talking about any fluids in microgravity. Although if you want to go to the space station, be an astronaut, you have to design experiments that can only be done in space. Then you say, I have to go up in order to look after my experiment, and then you apply. Okay. So let's just go through, this is going to be some thermodynamics. You said the word entropy, right? We're going to learn a little bit about thermodynamics today. And probably all fall asleep, including myself. So let's think about how gases move. Because we're going to start, we have to make a number of approximations in order to understand how heat and energy is transferred. So as a gas or liquid or fluid is heated, it expands. And it becomes less dense, and then it rises. Right? The reason that it rises is so that is the phenomenon, and I try and pound that into people and say hot goes up, well, why hot goes up? Why does less dense mean go up? Okay, you're like 97% of the way there.
That's severe.
Okay, you're saying the same thing, but there is a physical, remember that we're physicists, right? So, it floats is not a physical description. What causes the floating? Remember that in physics, things happen because of forces. Why less dense float? You're now describing less density. Give you a hint. Close, that was good. Just shoot from the hip, Okay. Nope. Very close. It's the only one that we described. What does it mean today? Pressure. What is a pressure? Force divided by? Almost there. Slide area. And so the trick to remembering pressure is currently I am wearing shoes, right? Or I guess I should say sneakers, right? And there's like a very nice pressure on the ground. If I were to be, say, on my tiptoes, what happens to the pressure? Goes up, right? I know that people who wear high heels know this better than I do, right? But let's say you're on stilettos all day, you have a lot of pressure on your toes. And like ballerinas literally get enormous, like fucked up bruises on their toes because of all the pressure. Whereas you never would have that from just walking. It's force divided by an area. Okay. So now we're thinking back in terms of forces, and here's a description of why force change. This force is changing with altitude because density. Density and pressure are the relationships here, and here is the physical interaction between them. You grab some parcel of gas, you expand it, okay? And it's supposed to be in hydrostatic equilibrium. That is to say, it's being pulled down just as much as it's being pushed up by the pressure below it. But if you make it too dense, then it can't supply enough downward pressure. And so it goes up because now there's pressure from below that is not being matched from the pressure that it is putting down on the gas. So it moves. That's why hot go up. Cool? All right. There. I hope this works. It's fun. Okay, this will go to the next one. Okay, so after it goes up, after it rises, it dissipates its heat. Okay, so by those actions that we talked about earlier, it gets rid of the heat that it brought with it. And that might happen on the process. That might happen rapidly and then, right? So there's two different ways to do it. And then it becomes cold and it falls. Okay. So that's why it's a heat exchange. Right? You're delivering heat from the lower part of the atmosphere up. Okay. So we're going to start with a small blob of gas. We're going to raise it without removing any of the heat. That would be an adiabatic transfer. Let it expand so that its pressure finally equalizes with its surroundings. And then, if the result is lighter than the ambient buoyant blob, you keep going. Let me break it down. There's some words in here, and we'll talk about this whole process of an adiabatic and non-adiabatic transfer. Let's just start by drawing a little blob. Okay, circle. And this gas is surrounded by other gas of the same weight. Let's start with the same weight, just different temperatures. Okay. So we'll take T, we'll make it hot here. We'll do T, and we'll make it cold here. Okay. So now I've heated up the gas. Now I am not going to allow the temperature to change in my little dotted lines. Okay. So what's the first thing that happens? Step one. Right before. What's the first thing that needs to change? The temperature just changed, and that causes a change in the almost there's one intermediate step between temperature and pressure. The density has to change first. Okay, so now I get a bigger circle with the same amount of heat, the same total amount of heat, right? But just in a larger area. Same number of particles. And now the density in here is low. So now the density has gone down, right? Compared to the external density was the same here. Right? Relative. And now it can go up. Okay, let's say it's up here. Let's not let it exchange its heat yet. Here's TH. Here's rho. This is the same rho, by the way. We're not letting it change size. Okay. And now let's check it here. So the question we want to ask is how do these two compare? Because we have a potential issue. If let's call this rho 1 and rho 2. If rho 1 is less than rho 2, what happens? What? If the density of rho 1, the blob, is less than the density of the surrounding medium, it would rise. Good. Okay. And if it's the same, yeah, stay there. Things out. Blobs move home. And similarly, if it is greater than, let's see, right? Okay. So this one is called what? Oh, this is called convection. Okay. And the easiest way to think about this physically is the idea that gas, because of the difference in density from the surrounding medium, goes up. Right? It gets to the top. Now it's met a medium with its friend. It gets rid of all its energy. Once it's gotten rid of all its energy, it may, for example, have higher molecular mass, right? Maybe it has a different composition than the rest of the gas, but now it's cold, and all of a sudden its density is greater than its surrounding, and it falls. Simple. If it's the same gas, let's say it raises up, and it passes through this region, it can overshoot and come back down. And it can do this. Let's say this is the 0 point. And that is a version of a gravity. That's not like black hole gravity waves, that's atmospheric gravity waves. And so we'll talk about that. Okay, so let's watch this cool video. I hope this fucking works. Let's go. Okay, where's the hot? Over prior stuff. That's it. Well, it's supposed to be too hot down here. Up here. And these little dots are your colds. This, for some reason, is the hottest part, but it's supposed to be. It's also supposed to be longer. I'll find a better one. But this is showing you colder, denser fluid falling, right? And the physics is the same, going up and going down are the same. Okay. There it is. That's the equation of hydrostatic equilibrium that we know and love. And we can sort of get this dependence of pressure on height. And from that, we now need to understand temperatures, right? So we use constant temperature, that's never really right. So now we have to understand how a fluid moving is going to be changing the energy, right? Okay. So we can create something like, if we look at a certain region and we say, hey, the conditions are all right for convection, you can create something like a temperature gradient, right? The TDZ means how does the temperature change the function of altitude, okay? And what we're going to do is we're going to say the very first approximation that convective heat transport is adiabatic. Now, what is adiabatic? Okay. Why can I make that statement about convection? Okay, let's think about the time scale, right? Let's take water. Okay. Water, let's say you have a bottle or a pot, clear pot of water. Okay. What temperature is the water? Don't apply any heat to it, just in your classroom. Room temperature. Yeah, room temperature. Okay. So it's emitting at what temperature? Yeah, room temperature. Room temperature. And what wavelength is it emitting? Infrared, yeah, it's in the infrared, right? And the infrared is very easily absorbed by molecules, specifically water. It loves absorbing the infrared. Okay, so the heat inside is very uniform. Any light that's being emitted is being absorbed almost immediately by the nearby molecule. Similarly, I have one very active water molecule. What does it do? It bumps into its nearest neighbors, and because it's fluid, they're all like, chill the fuck out. Every one of those collisions takes some energy from the fast moving guy and redistributes it all over the place. Right? So diffusion, for example, if I were to stick an iron poker or a very hot spoon, right, it would be slow. Right? It's a process, radiates heat not immediately through the water, but kind of just like slowly moves it from one edge to the other. And if I turn on the burner, I get some bubbles going, which of those three processes is the fastest at distributing heat? Very quick. Another way to say this, and the funny joke, right? Okay, someone farts in the classroom. Okay, why do you smell it? Is it because it radiated away from their butt? Is it diffusing away from their butt? It's because they went like that. Right? Okay, so the easiest way to get something from point A to point B in a fluid usually is motion. Now we can change some of those parameters. We can make them planetary scale, right, where we can make diffusion more effective. But on small scales that we might think about, usually transporting a piece parcel of fluid from point A to point B is the most effective way to do it. And you lose very little heat. Right? Because the two other ways of losing heat are not fast compared to motion. Right? You move very slowly, obviously diffusion becomes more important. Simple. Okay, so we understand adiabatics, we understand why we're doing this. You ready for math? Oh, there's. So that's a simulation. You can't quite see it here super well, but this is the surface of the convecting surface. And if you look on the side, you can see these are the places where it's cool and it's falling back down, the places where it's hot, blue, the light blue, right? And so it comes up, cools because it's radiating, and then it falls back down. Back up again. They're cooling for the cells, right? All right. Okay. Ready for entropy? What's entropy mean? Look, heat. Disorder, yeah. We can use it to describe how we perceive heat, right? But it's not necessarily the flow of heat, because entropy may or may not be reversible, right? So you can have processes in which entropy doesn't change. And so when we talk about statistical physics, we talk about conserving different parts or different quantities. Sometimes you can say that it's an isothermal process. That would mean that temperature doesn't change. Good. Sometimes you say it's an isovolumetric process. The volume doesn't change. Sometimes you say it's an isobaric, right? The pressure doesn't change. Good. Now, if I say it's an adiabatic process, heat is not exchanged with the environment. So if, for example, I think about the total heat as GQ, which is the energy and the PDV work, I can trade between them, but I can't go out, right? So an adiabatic process, by definition, all of the heat, right? So this says heat is absorbed by the system, but also if you emit heat, right? So then this dE, that's the change in internal energy. And what does dE mean usually? How do I interpret that? This is the PDV work here. The dE is internal energy. The internal energy is usually represented by what letter? For a gas, for example. How do I write the internal energy? How do I write it? What happened? What happened? H squared. H squared. 1/2, a kind of length. Could go with something like KT times a number. And depending on the degrees of freedom in that gas, you might have something like 1/2 or 3/2 or 7/2 out here. Right? Have you ever seen this formalism? This is the energy in a gas. I'll show you this. We'll come out. Okay, and the PDV work is work done by changes in volume, right? Good. So if we don't change any of the heat, inside of the box, inside of the parcel of gas, okay, then if I change the volume, what has to happen to the energy? Okay. By definition, right? Good. So, here I can say something like PV. I can use this disgusting formalism. So let's write this. PV is equal to N KT. Okay. If I take this and I turn this into a differential, I have to do the chain rule here. So I can use dP times V plus sorry. Oops. What? Yeah, or I can do P. I'm just gonna write it so that it's the P zone in the front. And that's equal to
K.
N K T. Good. Okay. Now this left hand side I have this thing. Right? I know that's equal to dE. So now I can write differences in pressure in terms of differences in temperature. As long as I understand this PdV work. Okay?
Does EPP also refer to work as well, or is that defined something else?
Yes, this is the PdV work, and this is the pressure, changes in pressure on the volume. So let's say, a way to think about this really, because we'll do this in fluids. So you have some box, right? Let's take a box with 4 sides. I'm going to make it not volume, I'm going to make the area. Pressure on a small part of the area. As you change the volume, you change the area, right? That is going to give you different amounts of work. As opposed to here, to keep the same volume, but now maybe I change the pressure. There's a differential in the pressure, right? Okay, so you can take all these derivatives, you can add them all together, and you can give them special names. So we're going to do that because it's going to make our life easier. If you go back and you see, let's just write these all out so that you can see them. Okay. So dq is not there. Good. Ran to around it. Right? DE.
It's the change in internal energy.
Right. Internal energy. DV. Volume. We know this question, right? Okay, my right. Okay, so now let's look at a couple definitions here. So what does it mean? dq dt. How is the heat transferring as a function of the temperature of the system? Right? And if I go in and I look at dq, how did I write dq before? Okay. So I can rewrite that, of course, to say dE over dt. And I'm being a little sloppy here because I need to hold something constant in these derivatives, or they are imaginary. So instead of the first one, I'm gonna keep dV equal to 0. That is to say, there's no changes in volume. And similarly, I'm gonna say there's no changes in volume. I'm gonna define this as the heat capacity with no changes in volume. That means at constant volume. So I call that C, heat capacity, at constant V volume. That make sense? Okay, this is just the definition. This is a material property. Okay, if I have a gas or a fluid, this is describing heat exchange. Right? How well am I going to hold on to my heat at a given volume? Okay. Let's look at the next one. I'm not going to write it all out. Here, I have the CP. This is again a C, which is a good. What kind of constant? What? Heat capacity. C is for capacity. Heat capacity here at a constant pressure. That is dQ dt. And here I've set dP to 0. So not allowing the pressure to change. Right? And what's nice is that these are related. All I have to do is take the CV and just add to it NK. Remember where NK comes from? Yeah, well, not just from the idea of gas level, like what these letters mean, what the N means. Yeah, K is the constant for sure, and then N is. Okay, and if I take the ratio of them, I get a really cool number called gamma. Okay, this is called the specific heat ratio, but you will learn it and love it as the adiabatic index. Because the adiabatic index of a gas tells you way more about the gas than you ever thought possible. Okay? So if I do, in fact, have an adiabatic process with dT, and let's go back one step. Remember how this was written? See this part here? Okay. So I can take this NK, I can put it on this side, so I have dT by itself, and I can reorganize them with these. Right? Then I can write that the differential in temperature can be related to PdV over Vc, or Cp. And this is a material property. Okay. So now we get to do fun things. All right. So I guess you haven't had this in stat math, right?
Never done this. I don't think so.
Okie dokie.
Yeah, we're at the closest.
Maybe I should keep it. Just like figure out what to get better. All right. So there is a very specific rule for ideal gases. And it's just that. Okay, so let's talk first about mechanical degrees of freedom. So what do we mean a mechanical degree of freedom? If you have an atomic molecule or an atom, let's take some arbitrary atom, okay, it can move in 3 directions. Which direction are those? That's what I said. Very good. So it gets 3 degrees of freedom. Okay. If you have a molecule, say a diatomic molecule, that is to say 2 identical atoms that are bonded, it can now do a couple extra things. What are those? It can rotate, right? How can it rotate? No, not the physical mechanism for how it rotates. Which we talked about. How can a single atom move? In what directions can 2 who are bonded together, how can they rotate? What other direction?
Fine thing.
And this way, right? That's 1 degree of freedom. This way, right? Okay. What about this one? Does that one count? Yeah, this should count. So you can do this, and you can do that, and you can do it at different rates. Okay, so that's 3 more degrees of freedom. Okay, and what else?
Still move in the linear direction.
Yeah, that's still this trend. So this is X, Y, Z. So that's 3 degrees of freedom. Then I have 1 more degree of freedom this way, and 1 degree of freedom this way, and then 1 this way. Okay, because that's different. What's the last one? It's not a rotation.
Is it like expanding?
Yeah, what's that called? Vibrate. Okay, right? So these are 7 degrees of freedom. And that's why you often see like 7/5. Right? Okay. I just did it so good. Cold diatomic molecular gas, right? N2. Okay. And the way you can do this is the mechanical degrees of freedom that can be efficiently excited. So what are you allowed to actually do? It takes a lot of energy to like make your atom vibrate, then J is not valid, right? Interestingly enough, J is 5 for N2, and so you get 7/5, right? For an atomic gas, like hydrogen, for example, right? It's 3 translations, right? We could show, if you want to, we can prove that too. A lot of stuff. Okay, so here you didn't have vibration, here you do, because it's nice and warm, and you get an extra degree of freedom, so that becomes a 4 degree. If you have this gamma, where did it go? This is your adiabatic index. This is also giving you this adiabatic index here. So, all right, this is going to be a little tricky to show you how to do this. See how I have CV up here? And it's JK over 2. This K is still your constant K, and J is your degrees of freedom over 2. If you go back, we can write these in terms of those quantities. Right? Because CP over here is CV over NK. Let me just show you. Because if you've never seen it before, I don't want you to get lost here. So your adiabatic index is gamma, and then CP over CV. Now, how can I write CP? According to the line right above it. CV plus NK over gamma. What's this one? Bring CV in, right? Is that fair? Okay. So that's how I write the adiabatic index, but I can take advantage of the fact that CV is JK over 2. Okay. So CV is JK over 2. It's not joking. Okay, let's do that. Let's put this in top and bottom. So now let's write our adiabatic index. JK over 2 plus NK over JK2. Okay. Excuse me?
So that here's something.
Well, so the N we're going to use is going to be 1 here. You'll see for an ideal pure gas, it'll be the density, which is K. But the K's are all going to fall out, and the 2 is going to go over there. So Can you see that or do you want me to do it? K, K, K. I'm gonna multiply the two, what, top and bottom, I guess? Yeah, so the two for two, that would cancel this one, this one. So then this gives us J plus two over J. Right? And this is by definition the adiabatic index. Right, so before we had to calculate these things from the properties, but now we can say, well, as long as we can understand the degrees of freedom from the gas itself, right? So if you're doing something like Boltzmann's distributions right now, are you doing that? You heard about these? Okay, so if you're trying to describe the mathematical properties of a gas, then in order to do a property, you have to sum up all available states. In order to sum up all available states, you have to know in which ways can it move, right? So the degrees of freedom come directly before states, right? In order to enumerate the states. Okay. So this makes this really straightforward for most gases. If you say, oh, this object is mostly hydrogen, then you know almost right away that it's 530. Right? Whereas if it's a warm diatomic molecular gas, such as N2, right? It's 4. Right? If it's a warm if it's a cold diatomic gas, then it's 7. Okay. Right. Okay. We're about to get fun. Where do I want to start here? Let's go back. We're going to. Okay, how do I motivate this without being scared? We solve a differential equation. Get us in the game. Get us engaged. Yes. We wrote a lot of really cool stuff about heat transfer, right? And we are thinking in particular about how this little parcel of gas goes from point A to point B, right? And we're going to say, let's do it adiabatically, okay? So the thing about that is that if I'm not allowed to exchange heat with the environment, then that can surely only happen through changes in the internal energy or changes in the pressure dB, right? I have to trade those two. So I have this beautiful little equation that says something like dE equals PdV. And then I did a bunch of stuff to it, and we described something called the adiabatic index. I still haven't answered my first question. How does the volume and the pressure, that little gas parcel, change as I raise it up? So let me write it out for you really quickly, and then we'll see if we can do it on our own. So before I just put it up there. All right. So we wrote something. Oh, let's go back one more. Here at the very bottom. Right? We wrote this. P dV plus V dV. That's a differential of the ideal gas line. And what we want to do with this piece is we would really like to say, second here. How do we write this in terms of the PDV work? Okay, let's write this here. So on the right-hand side, here, you see the dt for the adiabatic process? Let's go back one. So I write this now for the adiabatic process. Excuse me?
Right, thank you.
Yeah, maybe I'll say that again. So dt is derivative. But, all right. Okay, so now we're looking really good, right? Because now we can eliminate dt. And we have some shit that's only in terms of the shit that we know. We love doing differentials with shit that we know, right? So let's rewrite this top part. What is it? Negative n k. I'm gonna put CV over here just for clarity, and then what was the last part there? P D. Oh, look at how pretty we looking, right? Okay, how would we do? What?
So what we can do is that we can meet on the left side.
So you want to put this guy over here. You want to do V dP is equal to what? Minus P dV plus. Actually, hold on. You want to do something like this. Minus P dV, right? And then I'm going to do 1 plus N K over CV. That's what you love? That's your favorite thing of all time? Is that true? Is that your favorite thing of all time? How can I clarify this? This is that looks gross and I don't like it. No, I just did a whole bunch of work. And I feel like it's not really helping. Because I feel like just on the tangent about this stupid evaluation.
You could multiply CV, both sides of that, so you get CV over.
You want to do CV over here?
Yeah.
Like this?
If you multiply on both sides, like, and you may over CV.
On my board. My board. On the board. Yeah, this was always gamma, right? Is that true? Gamma the whole time? Okay, so this is really easy now. V dP equals minus gamma P dV. Hey, yo, let's go, baby. What's that mean? How do I do my math piece from here?
Integrate both sides.
Ah, almost.
You have to get.
Can almost integrate from both sides. There you go. Okay, so now what do you want me to do here? Write this one? Something? Well, don't do the integration. Just have me move them over.
1 over V
1 over V
D.
dV is equal to,
Sorry, I think I looked, but yeah. 1 over P, or who's the gamma? Just put the gamma in front.
okay, wait, which side do you want the gamma on?
With the P, so it would be like 1 over P with gamma.
Okay, so it's gonna be 1 over gamma P dP per chance. And there's a minus. Do we like it? Do we or do we not? Do what? Greatest that ever was. All right, we started off the day thinking about differential equations, and we'll end today thinking about differential equations. How the fuck do I solve that? Okay, can you tell me what the answer is before you integrate both sides? By looking at it? It's okay if you can't. I like challenging you because I want you to think, right? There's only a few, and especially for these, like, I don't want to say they're easy because these, took thousands of years of study, understanding. But these are sort of our rudimentary functions that a lot of the harder math is based on. So when we see something like this, we should have sort of in the back of our mind an understanding of how it works. That is to say, you know, I already understand this, hopefully. What is that? Natural law, right away, boom. So even before I go to integrate this, I know a little bit about it, right? So we are doing that. Oh, what is the answer? Excuse me? Natural log of V.
Negative. Natural. Yeah. No, no. Averages are constant.
The game is where? That's the claim. Is that it? Like that?
Solve for gamma.
We don't care about gamma. We want the relationship between P and V. Remember, gamma is a property, right? So like I can calculate that at home if I just know the acids. The thing I want to know is how big can my bubble get? Can I do that yet? No, this is disgusting, right? We're almost there, but this is gross. I hate natural logs. I don't even know what they mean.
Do you want to switch it to?
No. I would say multiply by m this time, so you can get rid of the natural.
Yeah, but that's not horrible, right? Okay. So it's not necessarily just multiplying by, it's raising, which is a different operation. So if I raise the entire thing on both sides, then I get a relationship between V and P. But what am I missing before we do that? Now we're running out of time, so I don't want to go too far in the weeds here. But what am I missing before that happens? Is this exactly right?
We have our constants of iteration.
Or constants of integration, right? And that's really important. Because these constants of integration are the things that are going to let us relate one thing to another. Right? Okay. So that was really good. You did almost all of it completely by yourselves. Here's your constant of integration. Right? That's the LMP. Now I put gamma on the other side. It doesn't matter. It'll just be nicer when it ends up on the other side. There's your constants of integration. And then we raise the whole thing. Right? Okay. And what happens to the first term here? P. Right? And I put all of the constants of integration on one side. And I put all of the values on the other. Because now I've created a beautiful, beautiful formula that says P times V to the gamma is a constant. And so I can describe anywhere in the fluid, if I move this thing adiabatically, that the pressure and the volume are only going to change like this with respect to the adiabatic constant. Okay. And we'll see some applications for that next time.